is the Cartesian coordinate system. All that is a coordinate grid. That's the XY coordinate grid in which you can plot points on. Okay, so it just gives you a little bit overview of actually the person that created it. But the one thing that you need to know is what the origin is. The origin is the center, okay, which is 0, 0 on a coordinate grid. It's dead middle, okay, 0, 0. So just kind of go through this and make sure you can read a coordinate grid. Okay, it says go ahead and label the following. So what is point A? So point A, what comes first, X or Y? Good. Points are written in this form, X and Y. So I am 2 over, so X is 2. I'm up 4, so Y is 4. So your point for A would be the point 2, 4. B, -3, it didn't move at all for Y, so what is it?
0.
Correct, 0. Okay, C looks like it's at 6, -3. D didn't move at all left and right, so your X is 0. -3. Okay, and then O, which is the origin, is 0, 0. Okay, how many of you guys know what quadrants are? Okay, Spencer, what are they?
Square is split up into 4 quadrants, so it's the 4 squares.
Good. Quadrant 1, quadrant 2, quadrant 3, and then quadrant 4 is how you label them. 1, 2, 3, 4. We start with 1 in the top right because that's where everything is positive. That's our most friendly quadrant.
Can we draw normal numbers?
Sure. Those are called Roman numerals, but that's fine. Okay. Write the coordinates of the points in the second quadrant. So the coordinate of the point would just be E. And that point is -2, 3. Write the coordinates of the point in quadrant 3. Quadrant 3 had F, which is -4, -3. Okay, complete the following table using your positive, negative sign. So in quadrant 1, I said we start in quadrant 1 because they're both what? Positive. Quadrant 2, what switches to negative? X. Good, we moved left. Left means negative, we're still up. Okay, so what I mean by that is if I'm here, if I move left, I'm -X, but I'm still up, so I'm positive Y. Quadrant 3 is negative and negative. It's left and down. Quadrant 4, I go positive right for X, but I'm still down. So there's your signs for what they should be in each quadrant. Any questions about that? Okay, this is a review preview, so yes, this should be somewhat simple, so that's good. Okay, just describing a pictorial pattern. So the 3 toothpicks are used to form a triangle. A second triangle is formed by adding 2 more toothpicks. A third triangle is formed by adding another 2 more toothpicks, etc., etc. So you have 1, you had 2 toothpicks, now you have a whole triangle. You had 2 more, you have 2 now, 3 now. You can see it's growing the triangles with the pattern. So it says draw the next 2 diagrams in the pattern. So what would the next 2 look like? Well, they would be and then we'd have, whoops, draw this a little better here. So we have here, here, 2, and then we'd have 1, 2, 1, 2. So that's where we're at with that one. So we have, if we add 2 more toothpicks twice, so there's 1. Actually, I'm going to put it 1, 2. So that'd be the next one. And if I do that again, it would be, this one would be the next one. So here is figure 1, this is figure 2, figure 3, figure 4, we did figure 5, and figure 6. complete the table relating the number of toothpicks P to the number of triangles T. So number of triangles, 1, happens with 3 toothpicks. So that'd be this one. 2 triangles is 1, 2, 3, 4, 5. And so it's going up by 2 every time. It says represent the data from the table of the values on the grid. So I'm going to go and move it up just a bit. So this is going to go away, but I'll rewrite it in terms of the table. It's right here. Okay, so we're going to put the data on the grid. So the data on the grid is T is triangles. So this is my T axis, which would also be, essentially my T is my X. Okay, and then P is my Y. Okay, so T1 goes up to 3. So 1, 2, 3, 4, 5, 6. Okay, etc. 2 goes to 5. 3 goes to 7. 4 goes to 9. 5 goes to 11. So there you can see you have a linear relation because you can connect those dots in a straight line. Describe the word's relationship between the number of toothpicks and the number of triangles. So the number of toothpicks is double the number of triangles and then add 1. So it's double, then add 1 is the pattern. So what it's saying is I times 1 by 2, add 1 to that. That'd be 3. Times 2 is 4, plus 1 is 5. 3 times 2 is 6, plus 1 is 7. That's the pattern the whole way through. Okay, but why don't we join this data, why don't we join it as a straight line that represents all the values? Yeah, Aiden? That's good for the negative piece, but you're on the right track. Like, if I put it here, I can't have 1.5 triangles because we're counting whole triangles. So that would be the point, is we can only have whole triangles. Okay? We can only have whole triangles for this example, not 1.5 triangles. It says write an equation that can be determined the number of toothpicks if we know the number of triangles. So we just did that. That equation would be P equals 2 triangles plus 1. Double the triangles, then add 1. So what you can do with that, if you say, I want to make 20 triangles, you'd plug 20 in for T, and it'd tell you how many toothpicks you need. Okay, 20 times 2 is 40, plus 1 is 41. So in order to make 20 triangles, I need 41 toothpicks. Okay, any questions with that? Am I going too fast on some of this at all? Yep. No problem. Okay, make sure you have that equation. We are going to go ahead and use it. G and H is going to use that equation there. Okay. All right, so you'll make it. Here we go. So we're going to do now, we're going to use that equation we made. It says toothpicks equals 2 triangles plus 1. Use the equation, to find the number of toothpicks if there's 27 triangles. So this is a T. So we put that in for T. So P equals 2 times 27 plus 1. 2 times 27 is 54, plus the 1. 55 toothpicks is required to make 27 triangles. So conversely, if it says 83 toothpicks, where do I put those? Where do I put that number? I put it right here for the P now, and we're solving for T. So 83 goes over here, and then we have to solve. So I have to go minus 1, divide by 2. 41 triangles is how many 83 toothpicks would make. so I have 2 more examples. Okay. All right. Okay, so here, let's cut off, oh, there it is. Okay. Okay, so I'm going to have to read the top because I need the whole grid here. Okay, so the top says, students in physics classroom determine the resistance in an electrical circuit by measuring the voltage when a current amps was passed through the circuit. The table below shows the results. So here's a table they're building. So and it's written in this form. This to us is our x, this to us is our y. Because the current determines the voltage. Okay, the quick short lesson on that, guys, is that you figure out what's independent. Okay, independent's the thing that's not affected. So the voltage depends on what the current is, but the current, it doesn't depend on anything. Okay, so the current hits out the voltage. So represent the data from the table on the grid. So here, we're going to have our I is down here. And then our V is the vertical axis. So it's going by 0.5s. So we don't want to go by ones, because if I go by ones, I'm going to have to put really small slivers here halfway between. We want to use as much of the table as possible. Okay, normally, just because I'm down here, you can't see because this is black. I'm going to write what I'm going to do it up here. So let's see, how much do we have? We have 1, 2, 3, 4, 5, 2, 3, 5. So that's we have 20. So we have 20 squares, and I'm going to 4. So every 5 squares, I'm going to call a 1. Like that. So wait, there's 25. 5, 10, 15, 20, 25. Yeah, so every 5 squares is going to be a 1. Okay. So by doing that, I need to know, okay, if I'm doing 0.5, where would 0.5 be? It'd be directly in the center. It'd be right here. That's 0.5, half the distance, 1. 1.5 would be right here. Okay, so you're just going to go halfway between them. Okay, so we're starting down here, though. Like I said, the table starts down here. I just wrote it on top. You can write them down here. So guys, sorry, write these down here. I'm just not doing it because you can't see mine. So our first point will be right here. What do I want to go up by? Sorry. 48. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I want to go by 2s. Because there's 24. So I'm going to go by 2s all the way up. Okay? So, sorry. 0.5 would be right here. I'm going 2, 4, 6. My first dot's right there. I know it's hard to see there. I'm waiting.
Could you just move further down?
No. Well, I mean, your scale. Okay, so good question. So the reason I picked 2 is if I do 2, the top is 48. So this is actually the smallest scale I could use. I could go by 4s, I could go by 5s, okay, or I can go by 10s. But if you go by 10 stuff, you're going to be a little bit different. But we want to maximize the table. Okay, you can go by 6 if you want. That's fine. If you go by 6, your graph's going to probably end right about here. I'm using the whole grid. Okay, so it's up to you. So the scale does matter. Don't go by 1s, Raj. You can't, because if you go by 1s for this example, you won't get to 48. Yeah. No, it's a serious question. What's that? You have 50 counting up?
Yeah, it's 52 actually.
52? Okay, that's fine. So still by 2s is going to be the best fit. Okay, we'll get to it. That's not a problem what it goes by. We're going to go by 2s. Again, you could go by 6s if you want. You can go by 4s. Whatever you work best with is fine. But I'm going to go by 2s because all these are even. And I know if I go by 2s, it'll space my graph out so it uses the whole grid. Okay, so 1.5. So here was 0.5. So then here's 1. Here's 1.5. I'm going up to 18 now. 8, 10, 12, 14, 16, 18. So there's mine. My next point. Okay, 336. So 3 is right here. Mine's written a little bit to the side there. 336. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. So here's 36. And you kind of start to see that it's pretty linear. It's going in this, like all those points would connect on in a linear line. Okay, 3.542. 3.5 is just a little bit over right here. 42 would just be 3 spots up. It's right there. Whoops. Right there. I hate that it does that to me. Okay. And then 4 is 48. Yeah, so 54 and 52, you guys are right. So 50 and 52 would be right there. Okay. That'd be your line. And it says, does it make sense to join the points together with a straight line? Well, can you? Yeah, because you could have decimal current. Current's not a whole thing. Okay, if you're saying, well, what's whole versus what's not whole? Well, there's things that you can do. Current and whatnot and voltage, all those things can have decimal outputs. But if I was saying we're counting shoes, we're not going to have decimal shoes, right? We're not going to have a 0.2 of a shoe. So there's certain things that you can have whole numbers and connect the line. There's certain things you can't. This is one where you can.
You could have half of a pair of shoes.
Yeah, of course you could. Yeah. That'd still be one whole shoe, though. Okay, so that would be okay to connect that as a line there. Yep. Okay. Use a graph to determine the voltage. Guys, listen. Use a graph to determine the voltage at 2.5 amps. So at 2.5, what's the voltage? So that'd be here. My line's a little bit off, but I think it looks like it's going to be 30. Yeah. It's going to be 30. Okay, 30 volts. Okay, what do you notice about the pattern? What's it going up by? No. 6 is close. 6 is close. It's going up by 6 every what? Half. So what's it going up by every whole? 12. Good. So you want to use 12. Okay, so here we're writing the equation. It's going to be volts equals 12 times I, so your current. Volts equals 12I. So you can test that. So if you plug in 3, what's 3 times 12? The 36. And on your chart, that's what it says. It'd be 36. Use the equation to determine the voltage when the current is 6.2 amps. Okay, so I have to divide 12 here. Oh, wait, excuse me. Nope, I wrote the wrong way. You're right. Twelve times 6.2. I put in for the wrong variable on accident. I was jumping ahead. Okay, so that ends up being 74.4. Okay, the resistance is calculated from the equations V equals IR. State the resistance in the electrical circuit. So the resistance is 12. This is more of a physics thing, but the resistance would be 12. Those are called ohms. Just from R12. Okay. Okay, we good? Okay, where's the confusion? The ohms come from what our growth factor is. Our growth factor is 12. Okay. Sure. Okay, discrete versus continuous. That's what we were talking about. What's discrete versus continuous? So, class example 3, there's continuous variables where they can be broken into decimals. That's what I was talking about. They can be continuous. There's an infinite amount of possibilities for their answers. Okay, in class example 2, they were discrete because they're whole things. They're whole triangles we were talking about. Okay, you can't have decimal triangles. So in the following here, our last example is, what are these? Okay, so I'm going to call on people here. Okay, so Noah, let's just see here. Time taken to complete a 100-meter sprint. So everybody's times for running, would that be always whole numbers or are those decimal numbers? Decimal. Good, so this would be continuous. Does that make sense? 11.2, 11.26, 11.1. Okay, those are all be continuous answers. Okay, yeah, if you're fast, 9.4, sure. Okay, Ridge, number of students who passed Math 10. It's going to be, yeah. What's that? Okay, well, it's not a question. Is that continuous or discrete? Is that continuous or discrete? Yeah, that means discrete. Yeah, we're not going to pass half a Ridge and a quarter of Spencer. It's either you're not in or you're in. Okay? Height of students. What do you think, Isla? Height of students. Continuous, good. I don't like this example because you could argue this one that shoe sizes are set, so let's just say shoes. Let's just say shoes. Shoes, no. Discrete. Yeah, a lot of different types of shoes, but not number of shoes. Number of shoes is 5, 7, 8, 9. That's right.